In this section, which is the second section of Chapter 1, we're going to look at different types of data. In particular, we're going to talk about the difference between a statistic and a parameter, and then we're going to look at how data can be classified into one of several buckets, one of several types, depending on how it is presented. Let's discuss what a parameter is. In statistics, a parameter is any numerical measurement that describes a characteristic of that entire population that we are interested in learning something about. So in the previous section, we talked about the difference between a population and a sample. We said that a population is the entirety of all the people or all the things that we want to learn something about. A sample, on the other hand, is a subset of that population, and so a parameter is any numerical measurement that describes the totality of that population of interest. For example, let's say that I want to learn something about all of the adults in a particular city ages 55 to 65. Perhaps I find out that of all the 55 to 65-year-olds in a particular city, the average time that they spend walking outside for exercise is 33 minutes. And we'll look at that word average in the future. I'm using it loosely here for now. But as long as that calculation was made by including all 55 to 65-year-olds in a particular city, in other words, those measurements reflected all the data coming from the population, then it would be referred to as a parameter. A statistic, on the other hand, is a numerical measurement that describes a characteristic coming from a sample, which is a subset of our population of interest. So let's say, for instance, that I wasn't able to get information from all the 55 to 65-year-olds in a particular city, but I was able to get data for a sample of that age group from the city. Hopefully a random sample. We talked earlier, the sampling techniques do impact the quality of your data. But let's say that I was only able to get information from a subset of that group, a sample, and I found that on average the persons in that sample walked 49 minutes each day for exercise. Well, that average of 49 minutes is a statistic because it was calculated from data that came from a sample. Let's start looking at how data can be classified. First, data can fall into one of two categories, either quantitative or qualitative. So all data falls into one of these two buckets. Let's start with quantitative. You should recognize that the word quantity is related to this title. So quantitative data, also referred to as numerical data, has to do with quantities or with measurements. So anything that has to do with counting or with taking a measurement would fall under this category. So for example, the weights of supermodels or the weights of fruit in a supermarket, that is a measurement. You have to put the fruit on the scale and you have a numerical reading. The second example here is the ages of respondents. Age, of course, is measured in numbers, so that is something that is a count of the number of years, for instance, of any particular person. The other big bucket of what data can fall under is qualitative, also known as categorical data. The title should give you some clues. This is data that can fall into one of several categories. So we're no longer talking about counts. We're no longer talking about numerical measurements. We're talking about these buckets that data can fall into. So think of categorical data as referring to labels. And yes, labels can actually look like numbers, but if those numbers are acting like labels and not as counts or measurements, they would still fall under this categorical data classification. So examples, of course, gender, male versus female, that's not numerical, that is clearly categorical, but also shirt numbers on the jerseys would be considered categorical because those numbers aren't representing counts and those shirt numbers are not representing measurements. For example, we wouldn't say that a player who has a shirt number of 10 is 10 times better than a player who has a shirt number of 1. Those numbers really are labels. They are not acting as numbers do. They're not counting and they are not measuring. Now that we've talked about the two major classifications of data, quantitative, which is also numerical, versus qualitative, which is also categorical, we can kind of dig down a little deeper into one of those two branches. So let's look at how quantitative or numerical data can be further divided. Quantitative data could either be discrete or continuous. The way I remember this is that discrete data can only take on certain values, and then there's a gap or a jump between possible values. For example, let's talk about age in years. If we talk about age in years, and a person can be 5 years old, 6 years old, 7 years old, 8 years old, we wouldn't say, if we're just counting years, that a person is 5.297192 years old. So if we're jumping from one whole number to the next, that would be an example of a discrete measurement. Continuous data, on the other hand, these are measurements that follow a fluid measurement scale. So there's no interruption in what values can be taken on. Continuous numerical data, time, if we don't stop the clock, time is continuous. So yes, we can measure in minutes, and if we do so, now we're looking at discrete values. But if we allow time, such as in a race, to be clocked so precisely that we can get out into several decimal places, so that we can distinguish between one athlete and the other crossing that finish line in a very specific time, that would be one example of a continuous variable. Now, the example that I like to use in class is, think about people's feet. All right, so young children, their feet grow very quickly, right, in those early development years. The feet grow continuously. Now, they could grow more quickly and then slow down in growth in different eras, but we don't picture feet as kind of just going bloop, bloop, and just kind of going from one measurement to the other immediately. So it's a fluid, almost indetectable growth. On the other hand, when children go to shop for shoes, even though their feet are continuously growing, you can only buy a shoe size of 5, 5.5, 6, 6.5, for instance. So shoe size would be considered to be discrete, while foot length would be considered to be continuous. Here's another example of discrete data. Discrete data are countable, and as I said earlier, it doesn't have to consist of whole numbers necessarily. My previous example of shoe size certainly included half sizes. The key here is that from one possible value to the next, there is a jump, there is a gap. Here, the example is the number of tosses of a coin before getting tails. Clearly, that is a count. You can only take on whole number values, so that clearly would be discrete. As we said earlier, continuous data follows a fluid scale, and so values are possible anywhere on that fluid scale. You don't have those built-in gaps or jumps between possible values. So pretty much lengths are examples of continuous variables, continuous data, unless we specify that the length can only take on specific values. If you're a visual person like I am, you've probably taken some notes down throughout the last few slides that kind of has data at the top with two little branches, one that says quantitative or numerical and the other that says categorical or qualitative. And then from the quantitative branch, maybe you took out two more branches going down where you had discrete versus continuous data. This next slide is going to back us all the way up to the top of that diagram. Now we're going to look at all data falling into one of four different classifications. So let's start with nominal, the first of the four. The nominal level of measurement or nominal data refers to those categorical values. So nominal pretty much is synonymous with categorical. This is characterized by data that consists of names, labels, or categories only. We've already talked about this, so gender, on, off, yes, no, favorite color, all of those would be examples of nominal data because they are categorical in nature. The second of the four classifications is the ordinal level. Ordinal, of course, should be associated with the word order. So ordinal level of measurement refers to values that have a meaningful order, but that do not necessarily have a meaningful gap between one value and the next. And this one's a little bit harder to explain, so I'm going to give you some examples. Let's start with the one here on the slide. Your course grade, for instance, you can earn an A, B, C, D, or F in a course, and I think we all would agree earning an A is stronger than having earned a B, earning a B is stronger than a C, etc. So certainly the order of these letters has some meaning. However, the differences between each of these values is not meaningful. So the difference between an A and a B may not have the same meaning as the difference between, say, a D or an F. Now, if you're thinking about numbers, if you're thinking, oh, my 95 in the class, which earned me an A, yeah, I could subtract the 83 that somebody else earned to get a B. But if we're thinking about numbers, then we're no longer looking at just these 5-letter course grades. So, for example, I couldn't subtract B from C and have that subtraction be meaningful. So the ordinal level of measurement does have meaning in the order of the values, but there is no clear meaning between the differences of those values. So now we have the third level of measurement out of the four. This is the interval level of measurement. You can probably see that as we go from one level to the next, we're gaining something. So to go from nominal to ordinal, we gained meaning in the order of the values. I think we could all agree that if we back up all the way to the nominal level, let's say favorite color, and we had 5 possible values: blue, red, yellow, green, and I don't know, gray. So while those are the possible values, we wouldn't say that blue is greater than red or that gray is smaller than yellow. So the order of the colors is not meaningful. So when we move to the ordinal level, now we have data where those values have a meaningful order. In this third level, we gain something else. And what we gain is that now we have meaningful differences between values. For example, if we take a look at years, so the year 1000 versus the year 2000, the year 1776, I can subtract these values and that difference has meaning. For example, I can say that from the year 1000 to the year 2000, that's a 1,000 year difference. 1,000 years have gone by. From the year 1776 to the year 2000, I can say that's equal to 224 years that have gone by. So I can subtract values in the interval level of measurement, which means now I must have numbers, and those subtractions do have some meaning. Now there's still something that we are missing here in this third level, and that is there's no natural starting point. There's no natural zero. Nowhere where we can all agree the measurement begins. So in the case of years, if you think about the year 0, well, that's not when time began to be counted. That was actually a starting point based on historical events that was agreed on. There are other examples, for example, temperature. So if we're measuring temperature, yes, 0 degrees Fahrenheit seems to be a 0 starting point, but that's not where temperature begins. We can have temperatures that are in the negative degrees Fahrenheit, and so that's not the starting point. Let's look at our fourth and last level. So here we are at the ratio level of measurement. So in the ratio level of measurement, we do have numerical values that have a meaningful order. They also have meaningful differences between values. And now we gain that missing piece, which is that these values have a natural starting point. And so, for example, class times. A class can last 50 minutes, a class can last 100 minutes, so we can say that the class that lasts 100 minutes is 50 minutes longer than the class that lasts 50 minutes, and that would be true. So the differences are meaningful. We could also say that a class that lasts 100 minutes is longer than a class that lasts 50 minutes, so the order matters. But here is the difference. The time that a class can meet starts with 0 minutes. That's the minimum time, and therefore it does have a natural starting point of 0. Now, why that's important is that if we have a natural starting point, then now we can start computing ratios. I can actually say things like a class that lasts 100 minutes lasts twice as long as a class that lasts 50 minutes. So that phrasing of twice as long, that is a ratio, right? There's a 1-to-2 ratio in the length of those class meetings. To quickly summarize, nominal level of measurement, that's our categorical data. There's no meaningful order to the categories. In the ordinal level of measurement, now we have values that do have a meaningful order. Typically, we're still talking about categorical data. We use the example of a letter grade of A versus a letter grade of B, etc. But those values have a meaningful order. In the interval level of measurement, now we can subtract two values, and that difference has some meaning as well. However, it doesn't have a natural starting point of 0. And finally, in the ratio level of measurement, these are our numerical values that not only have meaningful differences, so we can subtract two values and have meaning in that subtraction, but we also have a natural zero starting point, which tells us that we can also talk about ratios. We can say things like, this is 3 times more efficient than the first. And that's language that can only happen if we have a natural starting point. This next very small segment on big data, I think deserves a lot more attention than we tend to give it in this class. Big data, if you ever hear that in the news media, refers to the fact that we are able to collect so much information that it is becoming increasingly complex to store it, to analyze it, to make sense of it. Think about this YouTube video alone. When this video is created and posted to YouTube, immediately it is consuming storage, and immediately it's going to start collecting analytics. I can go into my account and at any time look at how many views it's had. I can look at what day of the week it has gotten most views. All of those analytics are created and stored, and the wealth of information that already exists and that is being added to continuously is really overwhelming. So one of the challenges that statisticians have is making sense of all the information. Think about giants like Facebook, for instance. Think about giants like Google. If you do a quick search for a product, have you ever been a little bit surprised that you start getting ads for either that product or similar products? That's because all of your interactions are being recorded and they have algorithms set up to target you. So this is really, really big, and I know this is an introductory course, so we don't go into big data too much, but there are numerous careers that revolve around this growing area of big data. There are data scientists, there are data engineers, there are data managers. So if you have any interest in statistics, and hopefully you do after this course, know that there are many, many career opportunities that are first of all very lucrative because that kind of skill set is unique. So you'll have job security for sure, and also I think very creative, right? So it's not a job where you just go to make good money but you hate it. I mean, there's so many opportunities to do a job that revolves around big data that really speaks to your own personal interests. So I think it's a really good thing to think about. I've actually taken some data science courses recently through Johns Hopkins University, and there is a little bit of computers involved because of course the computers do the heavy lifting with the number crunching, but I really want to urge you to keep an eye out on those jobs that involve data analysis. I'll go quickly through these last two slides. First of all, just be aware that when we have missing data in a data set, we really should stop and think about why it is missing and then have a strategy for how to deal with it. If it's missing because the information wasn't reported, the information was entered in the incorrect format, those are different than information that got lost or that was intentionally corrupted. So data values that are missing just deserve more of our time and thought. We won't really have to deal with this in this course, but when you do have missing data, there are a few things that you can do to manipulate the data set so that you can still perform calculations. One is to just get rid of that missing data cell, so to speak, so that you can kind of treat everything else even. The other is that you can kind of put in a dummy value to substitute for that missing data set so that you can run programs that won't cause errors. And this is the end of section 1-2. In our next section, we're going to look a little bit more about the action of doing statistics.